Hello, everyone. Today we are presenting a key comparative analysis shaping for the future of rehabilitation. Comparative analysis of 3D printed smart orthoses for the dominant upper limb, material, components, and standards. This work was conducted by David Portilla Caicedo, Samuel Castillo Sanchez, Edna Avella-Rodríguez, Ramiro Plazas-Rosas, affiliated with the Industrial Control Research Group, GISI, from the Electrical and Electronic Engineering School in the Universidad del Valle, Colombia. This is our outline. These are the main topics that we are going to talk to you about today. Okay. Rehabilitation of the dominant upper limb addresses a significant clinical need. Using the Functional Recovery Index, we know that 50% of the patients are severely affected. They are unable to perform key tasks like dressing, feeding, breathing, and others. 30% are moderately affected. They require assistive devices or guided therapy. And finally, only 20% are independent and they regained autonomy in daily living tasks. Our research focuses on how 3D printed smart orthoses, by integrating materials, sensor, and standards, are advancing dominant upper limb rehabilitation globally. In our global research landscape in upper limb orthoses, we have that United States leads biomechanics and clinical trials, advancing intelligent exoskeletons and sensor technologies. Western Europe focuses on wearable cooperative robotics and biomechanical modeling for rehabilitation. Mediterranean Europe emphasizes design, innovation, 3D printing, and functional validation of passive exoskeletons. Asia leads biomechanics and clinical trials, advancing intelligent exoskeletons and sensor technologies. The Americas develops a robotic system, turboelectric sensors, and bibliometric analysis of post-stroke dysfunction. Finally, international organizations like WHO or UN establish global rehabilitation guidelines, prosthetic standards, and sustainable development frameworks. And our main methodology, we have four main blocks. First, device selection criteria. Here we study clinical relevance and technological maturity, the evidence of functional recovery in dominant upper limb, and usability in daily activities. Then we have our second block, analysis parameters. Here we study actuators and sensors, their precision, integration, and latency, the range of motion and torque, the materials employed, and the clinical observation like comfort, adherence, and functional performance. In third place, we have evaluation of material for 3D printing between polymers, composites, and recyclable materials. We studied durability, weight, mechanical strength, the energy efficiency, and sustainability. And in our last block, we have applicable norms and standards. Here we have the safety, ergonomics, and performance guidelines. We have the international regulatory frameworks for rehabilitation devices and the specific focus on upper limb orthoses. These criteria are essential to ensure clinical relevance, technological reliability, patient safety, and regulatory compliance in advancing 3D printed smart orthoses.
Well, now for the results, we have this chart that is analyzing the device performance. And in this radar chart, It shows clear trade-offs between passive and active orthoses. Passive devices cluster higher on attributes like comfort, usability, and obviously costs. Conversely, active devices extend further on adaptability and precision. For 3D printing materials, composites and PETG extend furthest in terms of mechanical strength and long-term durability. Meanwhile, TPU and recyclable materials cluster higher on formability, fit, and sustainability. In clinical outcomes, effectiveness stands strong. Usability remains moderate, but control strategies show the greatest maturity. Cost efficiency expands primarily in hybrid approaches. In the functional range of motion or ROM, values define ADL thresholds, such as 0 to 130 degrees for shoulder flexion and 0 to 150 degrees for elbow flexion. This sensor metrics helps assess suitability, uh, noting that the 3D motion capture ensures precision, IMUS extend monitoring, and goniometers remain reliable. In occupational tasks, we see complementary strength among rehabilitation modalities. The reduction of deltoid electromyographic activity (EMG reduction) dominates the reaching tasks. 3D orthoses provide necessary support for lifting. Teleoperation excels in overhead tasks. And lastly, home therapy balances assistance across various functional domains. In global guidance, such as WHO Rehab 2030 and community-based rehabilitation CBR, reinforces national policies. These frameworks translate into specific upper limb rehabilitation targets, including pilot exoskeletons for shoulder offloading and orthosis integration for elbow roam. However, adopting barriers persists, particularly at lower technology readiness levels like TRL 6, concerning equipment and training.
Okay. When comparing conventional devices versus 3D printed orthoses, we can see that 3D printed orthoses demonstrate improved fit, ventilation, weight, comfort, and compliance. In contrast, conventional devices remain heavier and less customizable. The convergence of clinical demands and technological modalities is shaping the future of rehabilitation. We highlight three complementary modalities for upper limb tasks. First, teleoperation excels in overhead shoulder tasks, providing intuitive control for complex movements and reducing muscular strain. Then we have customized 3D orthoses that stabilize elbow lifting, ensuring structural support and patient comfort. And finally, we have home-based therapy devices that sustain wrist rehabilitation beyond the clinic, promoting adherence and independence. This innovation is thus defined by the integration of patient-centered design and technological readiness. Okay, sustainability and digitalization are essential complementary pillars for scalable rehabilitation systems. Additive manufacturing, depending on the material and design for disassembly, can reduce material waste and energy use, and potentially increase recyclability. Clinical literature consistently reports improved fit and personalization in 3D printed orthoses. Finally, we have that digitalization pathways include workflow automation, scan, design, print, a digital traceability, parametric personalization based on patient data, and connectivity for remote updates and cloud integration. These digital capabilities are crucial for achieving scalability.
Now, in conclusion, smart 3D printed orthoses have demonstrated their capacity to transform the dominant upper limb rehabilitation globally. These devices achieve functional reliability, clinical usability, and patient centered safety through the integration of advanced materials, embedded sensors, and standardized protocols. This convergence of innovations and clinical relevance positions them as a global benchmark for rehabilitation practice. Finally, sustainability and digitalization are essential complementary pillars for a scalable rehabilitation system. Additive manufacturing reduces waste and energy demand and enhances recyclability. Digital pathways, automation, traceability, personalization, and connectivity ensure readiness for mass customization and policy implementation. These dimensions establish upper limb orthosis as eco-responsible, digitally enabled, and globally scalable solutions for the future of healthcare. This is our bibliography. Thank you so much for your attention.
Thank you so much.